give a talk at this. So today's talk will be maybe a bit algebraic representations here, but I will make some links with geometry, maybe with some higher infinity algebras. You will see how to go here in the context and what will be done exactly. So I will recall what is a Clifford algebras, what is a Cartan theorem in the introduction. So first, I will give you a brief introduction of what is going on from algebraic point of view and formulate the main results, and then we will discuss how they work. So later, we will start with first step as classical Hopf-Cajou-Samuelson theorem that describes the homologies of the simple compact group G. Things are connected. So we know that it's isomorphic to the cohomology of Lie algebra with the trivial coefficients. The same is isomorphic to the invariance in the exterior algebra of our Lie algebra. And this is again some exterior algebra over some space of so-called primitive invariance. So this is the content of this Hopf-Cajou-Samuelson theorem. You see the geometric meaning, so it's a direct homology of a group. And this space of primitive elements is defined you can define it in several different fashions. For example, it's one of the origins of Hopf algebras, and you can define the space of primitive invariance as a space of primitive invariance here, primitive elements of coproduct. In terms of coproduct, but you can also define it in terms of augmentation ideal and the corresponding orthogonal decompatibility. So if our Lie algebra is simple, then we have a non-degenerate symmetric bilinear form, for example, Killing form. This Killing form could be extended to the whole exterior algebra by this formula. You take contractions, T is the transposition, you just reverse the L monomials in your algebra, and 0 you just project to scalars. So it will be a very nice, well-defined form of the exterior algebra of G. So, and this sum will be direct sum decomposition. So, in other words, our primitive guys could be also seen as square orthogonal complement to the square of augmentation ideals. Well, you should also keep out constants.
Can I ask a very simple question? So, in the first line, the first thing for it is averaging over the. There is like averaging over the.
Or using the left translations. So you use left translations and then you use right translations to show that it's invariant.
And the second, the middle equality or.
So you know that this cohomology should be bi-invariant, right? So by using left translation, you will get to the identity. Identity will identify it in this exterior algebra of G. Your forms, now you know that they will be also invariant from the right. So this is basically the second end. There is some details.
Okay, thanks.
So the structure constants will always be an element of this cohomology, right? I'm just trying to find obvious example.
Yeah,
elements of this.
Oh, this, for example, I will show you. So it will be always 1, then it will be an element of degree 3. So it's called Cartan pretensor. Yeah.
That's the one.
For like for SU2 or like any group with the interpretation of the structure constant.
Well, yeah, okay. By structure constants, you mean the skew symmetric free tensors that obtain.
Yeah.
Yeah, we will see on the next slide.
And any more exotic example?
So I will comment in a second the whole structure of this.
Okay.
So first, this guy, or there's a equivalent formulation in terms of Hopf because the space of primitive elements has a natural iteration. Well, you just look at the degrees, and these degrees, they all odd. Moreover, the content of the theorem tells you that. Well, the number of this mi is exactly the rank of your Lie algebra. And these guys called exponents, they also appear as degrees of symmetric invariance. So invariance is a symmetric algebra, which are much easier to describe using some algebraic geometry techniques. Or, for example, High-Chandra. For example, for SLM, we will have something. So it will be one-dimensional guides, and usually they are one-dimensional except for O series. Then you will have a so these graded components in 1 degree you will have dimension.
And I guess the last equality uses the fact that the wedge GG is a co-commutative topology.
So this is a bit tricky to. It's a harder step to prove because this coproduct is not inherited from the coproduct on wedge of G.
Okay.
You need to prove the last equality. You need to use some Hodge decomposition and functoriality of.
But then you use this kind of what's the name of the theorem? Is Cartan? Yeah, Cartan or someone that said that the Hopf algebra is just similar polynomial algebra on its primitive element.
Maybe,
but it's like
it's easy. It's easier.
Okay, here is it. Okay, you don't use the Cartan element
because well, basically Hopf algebras appeared when the spring is.
Okay, I see. Thanks.
All right, so this is a classical setup. And then around 20 years ago, maybe more, Boston formulated a similar result for Clifford algebras. So as I said, we have now not the general invariant linear form, let's note that we can speak about quantization of the exterior algebra with respect to this form. It's actually quantization of Poisson structure given by this form on the exterior algebra. So it's some picture deformation given by this formula, which is the fixed notation. We also have this Chevalier map that is isomorphism of vector spaces, moreover isomorphism of G modules, but not algebra. So obviously, because one is supercommutative and another is not commutative. So we have a filtration. It's compatible with the standard filtration, and Boston proves the following theorem. So again, remember that invariance is exterior algebra on space of primitive elements. Here, invariance in the Clifford algebra of G, at Clifford algebra on the space of primitive invariance with this little bit twisted form. So, what is the theorem? So you take a contraction and then you project the scalars. You need a scalar for a form, right? Mm-hmm. That means you can also think about it by taking determinant. You know, the standard values. And we will try to generalize this result to the case of symmetric pairs. So corresponding compact symmetric spaces.
So what is BTL then? Oh, sorry. Yeah.
So it just differs from the previous form by plus and minus on certain gradation points.
Okay.
Yeah, because one. So what we are trying to do, we are trying to step forward to speak about symmetric pairs and the corresponding symmetric homogeneous symmetric compact symmetric spaces. So we start with symmetric subalgebra, some fixed points of some involution. We fix this decomposition. So we have a symmetric subalgebra and isotropic representation. And this is direct sum decomposition because we assume some conditions on this involution. So typical examples comes from real reductive groups or compact symmetric spaces. So I will force further notation. Let's choose a Cartan subalgebra in G such that T will be Cartan subalgebra of K and A will live in P. So it's one of the choices. This is usually called fundamental subalgebra. You can also speak about maximally split when you try to move as much as possible of H into P parts. Here, we are trying to do the following. We take Cartan subalgebra in such way that we try to maximize its intersection with K. Yeah, real reductive group, compact symmetric spaces. Now, this is recording for our Casual-Sanderson theorem. For symmetric pairs, the corresponding theorem is called Cartan's theorem. And the statement is the following. We'll look at the K invariance in the exterior algebra of our isotropic representation. Then it will be again some exterior algebra tensor is commutative algebra. So this commutative algebra now generated in even degrees. It's called characteristics of algebra. And it's usually, for example, when you speak about very nice symmetric space, for example, gross magnets, this will be exactly algebras that give you sugar couples. And this guy is a bit tricky thing. It's a some subspace which is realized inside of this invariance. So it is not a subspace here, but this is algebra. And this is a tool to compute some equivalent cohomology, and moreover, if it has a corresponding compact symmetric space, it's exactly the cohomology ring percent. So our goal will be to generalize this result to the Clifford algebra with appropriate representation and update this result, because this is a bit unsatisfying, because, well, this is isolated, but we want explicit realization. So we will define later primitive invariance inside of this exterior algebras that give you exactly the cohomology classes. All right. So how we can do it? Well, first step in formulating this result will be very easy. To prove some algebraic isomorphisms, recall that Clifford algebras are very simple. They have only one or two modules, which are called spin modules. So the endomorphisms algebras of these spin modules. And this spin modules naturally has a structure of a K module that can be described as follows. So let's look at two root systems. So we look at the not whole Cartan subalgebra in G, but at this part that Cartan subalgebra of K. So this guy will be not necessarily restricted root system, meaning that root subspaces will be not necessarily one dimension. But it's still root system is here nicely. Now, so we can consider the corresponding while groups. They act on the same space. Obviously, this is a subgroup here, because this root system is bigger. So we can look at minimal length because it represents this. Let's do the debate. Then results, I'm working back probably to Christianga, that the spin modules for isotropic Clifford algebra of isotropic representation could be decomposed as follows. So they have the following K action. So this is the multiplicity space, so action is trivial. And here is the corresponding highest weight modules finite dimensional is the following highest weight when rho is a half sum of positive roots standard. So here you should add, it will change your. So it's give you a complete decomposition of K types inside this. That's why we can easily formulate the following theorem with one additional component. So let's consider this very simple algebra of projections. So it will have as many generators as elements as W1 with a nice multiplication. So it's just algebra of projections on the one-dimensional subspace. Then you can prove, and I will choose proof, that we have this isomorphism. So we have a Clifford K invariance in the Clifford algebra of isotropic representation is isomorphic, but not as a Clifford algebras. This is just isomorphism. As of abstract algebra of Clifford algebra of A, remember that part of the Cartan subalgebra that leads in P. And it's algebra of projections. Well, how to prove it? Well, we know that Clifford algebra is endomorphisms of a spin module. So K invariant endomorphisms are here. Then you apply this decomposition, and you know from Schur's lemma that what you will have. You will have a projections on every K type, and then multiplicity space will give you endomorphism algebras. So this will be exactly this. Where A plus is the maximal Lagrangian subspace. Okay. So nice result, but not quite satisfying because, well, obviously filtrations here doesn't match. Here you kind of don't know filtration yet, and I will not comment about it. That's a very nice topic, but it's another paper. Here, filtration degrees are obviously smaller because recall I told you that degrees here probably will be much higher. So we need to introduce some new filtration here and here. So the rest of the talk will be about it. And unfortunately, here we cannot use many techniques that Cartan was using. For example, with no obvious Hopf algebra structure because of this guy, there is no Hodge decomposition, etc., etc. So now I will we'll make some assumptions about our symmetric pair, but they are very natural because in other cases we will not have the dimension of A will be 0, so it will be not interesting. So the cases when dimension of A is non-zero are precisely this one. I will call them primary and almost primary by some reasons that I will not mention. But basically, it's written that there is only one k-type and two k-types.
Can you remind us what's A?
A was, so we had a Cartan algebra of A, of G. It decomposed into Cartan algebra of K. And the part that lives in P. Right. So, for example, if you look for symmetric pair corresponding to Grossmanians, we know that the corresponding K will have the same rank as G. So the A will be 0. So, for example, for all Hermitian compact symmetric spaces, A will be 0.
Okay. And sorry, that was the first. Yeah, that's the first. No.
No. And this is the guys when it's non-zero.
It's not 0.
Assuming that G is. Okay. There is only 4 cases. So 2 families and 1 exception. And then we can formulate the base theorem. So it's more or less as you suspect. So first we say that we'll look at the primitive elements in isotropic representation. So we can restrict primitive elements for our G to isotropic representation. Nobody promised that it will be, for example, non-zero, and we will prove it later. But this is, in our taste, is a proper definition of primitive elements, and it's a bit better than some subspace because this lives in the exterior algebra of isotropic. And then the main theorem, well, it's analogous. I know probably you can skip this part, but you can describe the invariance in invariance in the Clifford algebra of isotropic representation in the manner that's the same as constant solid class. So we have some part which is Clifford algebra again. Now this will be filtered algebra isomorphism because these guys will have a higher filtration degrees, degree 1. And the filtration here is described in very natural manner, but it's behind scope of it. So there is a nice generalization of this result. Right. So, and this is the analog, the Cartan theorem was description of invariance in the Clifford algebra, in the exterior algebra, or homologies of the corresponding symmetric space. And here is a Clifford algebra analog. Note that we actually can prove this theorem without referring to original Cartan theorem, and it gives a new way how to prove it in very natural manner, I would say. So I will now discuss some tools that we used here. It is theoretically interesting for the audience. So we'll speak about Weyl algebras and transgressions. And first, the main tool is a G differential algebras. It's a framework introduced by Andrey Krutov. So we start with a V algebra. We look at the Grassmann algebra with different operators. We construct some Lie super algebra that will control our Cartan calculus. So we have some contractions, Lie derivatives, and differential. It all corresponds. Suppose you have a G manifold, you have a generating vector fields, then This guy will mimic contractions with these generating vector fields. This guy will mimic Lie derivatives along these vector fields, and differential will be direct differential on the space of differential forms. So why it all works? Well, we have these identities, and the main one here is a Cartan symmetric form. So the elements of this Lie superalgebra behaves like you expect from Cartan elements, and the corresponding Lie derivatives and contractions.
So I'm confused on the second line. What is the data?
Sorry?
Grassmann algebra generated by
One element.
a single element.
Yes.
Can you find the differential? Who goes the differential acts?
Well, here, it's a differential with respect to the generator. It's very easy. So we have one generator.
Yeah. That's extended by derivation.
Well, you know, and I actually defined it on the playtest, right? It's very simple algebra. It has to, but again, the Grassmann algebras are free commutative algebras, so you can define it derivations on generators and then input. And it's easy to see that with differentials with even squares.
So this is not by a single, just a single element.
Just by the single well, we can play this game with small guys, but you will construct something bigger, but then the geometrical interpretation will be, I don't know.
So where does the C live in this -101?
Well, it's here. So iota x is basically C times or x with respect to this.
Oh, sorry. On the left-hand side, you have a tensor product.
Yeah.
I saw it as a sum. So.
No, sorry.
Okay, tensor product. So that's this is just the thing you really explain.
Can you say that this is like a central
Yeah.
of the problem of the
Yeah. Yes. Yeah. Okay. Well, it's almost a simple extension. It's you add the derivation. You add an outer derivation, but you can complete to double extension, and that was Hubble was doing with the paper. But yeah, this is basically this homologous business and so it's a general.
So lambda psi is two-dimensional. Is lambda psi two-dimensional?
Yes, yes.
Okay, thanks. If you hear me, sorry.
When you take the direct sum of the CD, you're just taking the subspace of the endomorphism.
Well, I have a vector space spanned by
Two-dimensional. Yeah.
this two-dimensional vector space. I take it.
Yeah.
That's a product with my algebra, and then one-dimensional
And then one-dimensional space.
space spanned by this guy. And then I say how they interact.
But what does it really matter that it's differential? I don't see how the.
Because when you can, one of the realizations of this algebra is that you take differential forms on G manifold, then this D will map to direct differential. Lx will be Lie derivatives with respect to with respect to corresponding generating vector fields interaction, and contraction will be contraction with respect.
But that's actually justifying the algebra. It's just a one-dimensional vector space, and then you're defining.
Yeah. Well, you're asking why it's like this because when you want to unpack these commutators, you can actually use that D acts on psi by derivation. Okay. So you can use this information to derive the brackets.
R. What so they could just take that's the definition.
Yes.
Right.
Let's move further. So the G differential spaces are representations of such algebras, and G differential algebras algebras such that they have a structural representation plus all structural maps take values in the derivation of algebra. So in particular derivation, one of the examples of a G differential algebra is differential forms derivative. And of course, we can add the action of some group. There's some technicalities, maybe I don't have time to explain it, but you can imagine that the action of a group can be plugged in very natural manner. So what we can do, we can speak about some basic subspaces. This will be, for example, if you look at some principal bundle, then the corresponding G-basic subspaces of differential forms will be forms on the invariant forms in the base. Another example, very algebraic here, it's exterior algebra with the structure map. So you have a coadjoint action for Lie derivatives, constructions are defined as you expect by evaluation, and the differential is given by the closure form. So it's differential of this the algebra homology with trivial coefficients. And for complex symmetric spaces, we have this isomorphism. So if you take K-basic subspace of this G differential algebra, then we will get the homology of this space. All right. And the restriction of a differential here will be zero. So that's why it's even whole cohomologies. Because when it's non-symmetric space, then you have a non-zero differential here, and you should compute cohomologies to get cohomology of symmetric space. So this is one of the simplification. Now what I will need? I will need some alpha map, which is basically a quantum moment map. It's described as that. Suppose you have a module over the algebra with some form, then you have, sorry, it should be not add, but just an error. So that means that your Lie algebra could be embedded in orthogonal Lie algebra that preserves its form, because your Lie algebra preserves its form. Then we know as vector spaces it's isomorphic to the second degree exterior degree, and using Chevalier map we can send it to the Clifford algebra, and we can extend it by universal property to the algebra map. And for example, this will make the action of our algebra L on this Clifford algebra to be Hamiltonian. So we can just take supercommutators in this case. So that's why it's called quantum moment map, but it's also will fulfill definition that was given by Newton. And for in Hopf algebra matters, it's called inner action. So it's a generalization of the adjoint action of the Hopf algebra. Now, going back to our examples of cohomologies, here is the structural coefficients that you were speaking about. So, Cartan free tensors. There is a very nice element in the exterior algebra of G. So this Cartan free tensor, given but here is the explicit formula, and it allows to construct differential on the Clifford algebra of G in the following manner. So here, the differential will be given by the commutator with this guy, contractions commutator with linear guys, and Lie derivatives as commutators with quantum moment maps. And then one of the ways how we can reprove Cartan theorem is if we know how to describe this invariance, we just take the associated grade. That's we're going to do. Right. So now the collection of Weil algebras, which was used as a models to study principal bundles. So we look at the tensor product, and we define the G differential algebra structure by following rules. So we have a Lie derivatives, just extended coadjoint action. Contractions here acts on the exterior part, and as a differential, we choose this guy. So we start with Chevalier and then differential. So we can look at this guy as the algebra cohomologies with values in the symmetric algebra of G. So there's an explicit formula for this. When Hans knows it, it will be curvature variables, and I will explain why later. And we also have a control differential. So the just takes generators from here and send it here. So in fact, you can formulate it as some casual algebra, but if you take go later, as you. So with this structure mass, it will be G differential algebra. And by direct computation, you can see that this is this subspace of a kernel of differential. We can define the projection along this fragmentation ideal for the symmetric algebra, which will allow us to define the transgression map in the following manner. So using some homotopy methods, you can actually explicitly construct homotopy and compute these cohomologies. You see that it's acyclic, and because differential is invariant, equivariant with respect to action of G, you know that it's the cohomology class is given exactly by constants that embedded there. So that means that if we'll take some element of the kernel of differential, for example, this one, we know that it's invariant. We have that there the kernel of differentials, and because of this statement, because this algebra is cyclic, we have a corresponding chain for this element. So also in the image of differential, because differential is equivariant, we can choose invariant chain such that this holds. This chain is called chain of transgression, and then you can define a transgression map from this space to invariant in this exterior algebra by the following recipe. So you take element, you go to the corresponding chain of transgression, and then you project. So it was constructed, I think, by Chevalier in ICM talk. It was one of the ways how to compute cohomologies of exceptional limits. Yeah, so this defines this transgression. We will generalize this to the case of symmetric spaces. So yeah, as I promised, it's a theorem by Chevalier. We can speak about the some primitive invariants in symmetric algebra. We'll define them. And these they could be defined in the forward in the same manner as complement to the orthogonal complement to the square of augmentation. And the transgression map satisfies the following statement. So it's basically provide you isomorphism between symmetric invariants and invariants, primitive invariants in the exterior algebra. Let me recall you that to compute these guys in general is much easier. You can use Christian isomorphism, and then you look at your favorite book on the algebras. Somehow it's much harder to work with exterior with this. Okay.
Sorry, you said that you use this to calculate the cohomology of exceptional groups.
Yes.
How we?
Well, because you know that after you prove this theorem, you can easily compute the primitive invariance for exceptional groups.
Okay.
Symmetric map.
Okay.
Then you use the transgression map and you got information about primitive exterior invariance. Then you use Koch-Kazur-Samuelson's theorem saying that the cohomology of these exceptional groups are exterior algebra on this guy.
Okay. Like I mean, like this allows to calculate
Yes.
like for any kind of
Yeah.
all simply algebra. It's just exceptional ones are like not known.
Yes.
Thanks.
Because for us we use some tricks, but for exceptional algebra we don't. And then he used it in this theory of principal bounds. All right, and then I recall that the space of primitive invariance will be just dimensional or rank of our image. You can quantize this theorem, which brings you to the work of algebraic Dirac operators. It probably was obtained firstly by Chandra, but formulated later by Logan, and also as a G differential algebras by Alexeyev and Manrikin, and they applied it to some non-commutative equivariant homologies with some various coefficients. But you can quantize this picture, so you can think about the universal enveloping algebra as a quantization of symmetric algebra G. And Clifford algebra, we already discussed it as quantization of G. So now here you will have a Dirac operator. It's a cubic Dirac operator that usually works with constants and some physicists that I don't remember. But constant is more, it's usually more famous. And it will be again G differential algebra. Construction as before. Differential is defined by supercommuting is a yes, I think so. Yeah, it was several things. And it was somebody else, so but constant paper much more things. So besides them, yet. So it's another this cubic Dirac method to give you differential here, and then also when you want to speak about homogeneous spaces, some variant of it will be could be realized as geometric Dirac operator of the speed manifold. It's a very nice project to study such things. So it's a G differential algebra, and we can there is some Chevalier, which is quite tricky to construct. So it's a combination of a Chevalier map and Duflo map. So I will not write its precise formulas, but it tells you that the chronology is the same, which means that if you define this projection, you can define the transgression map now with values in the Clifford algebra in the same manner. Moreover, you can show that there is nice these maps satisfy these properties. So you have transgression map now with values in Clifford algebra and defined by the same formulas basically. And then there is some nice proposition by Cartan that if you take some primitive invariants, take a contraction, this will live in the image of this in the image of the quantum moment map. It will matter later. And actually, in the paper, we found a much easier proof of this statement. But let's see, we'll go to that. So, how to prove these things? What is the main tool, and how this algebras, different values could be formalized in a similar manner? So, the concept was due to Meindeck and Alexeyev. So, it's not commutative file algebra. It's a name a very terrible because there is a quantum. Commutative, non-commutative, and then we also have some uniformation of them. So this is, I think I don't need to recall what is a sheet in this audience. So we can look at the following tensor algebra. So we take our Lie algebra and change the degrees of it. So these guys will be odd copy of it. This will be even copy, and that's the corresponding degrees.
And what is T?
Tensor algebra over space. Okay, so basically, I want to do some casual type algebras. So in what follow, I will use the following notation. Phi will be a basis of even part, and phi bar will be a corresponding basis of odd part. One degree 1 points. And the differential here could be written as just a Joule differential. So it starts with you take odd generator, you produce even generator, and even generators find the curve. And then you expand it as a differential. You can construct. So of course it will be a module over G, so it will give you leader axis. And contractions will be contractions with the guys here, defined as contractions. So, how it's connected for a previous business and why it could be useful tools for some So we can speak about connections in the differential algebras. So it will be an out of a connection in the on your G manifold. So by definition, a connection on a G differential algebra is odd linear map that satisfies the following conditions. So that's basically is and so you have a connection form. these values in the corresponding VR. And the curvature of this connection is given by the formula as you expect. So, for example, we have a connection on non-commutative file algebra given by simple formula. So we just sent the copy of G star to the spot version. And the curvature components of the curvature form is given by these four variables. So here CIAB is just structure constant of G. So you have another set of generators given by the odd generators and these curvature variables. And I believe this construction can be generalized for any L infinity instead of this. So you have differential as one product, graph that has two products, and so on. It's just a set of malware Cartan.
Sorry, can I ask?
Yeah.
If you take forms on a Lie group, it's a G differential algebra,
Yes.
is a connection just a connection on?
Yeah.
There cannot be any like cubic moment, cubic, because you have is an odd linear map, so you have like a cubic part of the moment map. It will not happen. The moment map.
Yeah. No, it should be odd maps. No.
It will not have you say it doesn't.
So, but what connection do you want to start? So,
And I'm asking, if you just look at this with the definition and find two forms on a Lie group, whether you just require normal connections or there is something more exotic. Where it's not connection.
But you want to apply the principal bundle, not for group, right?
well, you can also for principal bundle, yeah, you can also do that. So with the forms on your group, you also do have form.
Yeah, but like if you want to recover the usual connection on principal bundle, then you could.
Yeah, yes. Okay. So this is the role of these hat variables that appeared before, and moreover, all our Weyl algebras that appeared before are quotients of this guy. So that's why if you recover information about this guy, we can play some nice commutative diagrams. Then the theory of transgressions could be formulated in the following manner. So you start with some G differential algebra with a connection. And there is a nice universal property of non-commutative algebras that if you have such an algebra with connection, then there is a unique characteristic homomorphism from non-commutative algebra such as G differential algebra, which satisfies this property. So it's some connection to a connection. And then, assuming that connection on your algebra is flat, so the curvature is zero, you can define the transgression map. So here you look at the special elements in the G differential in the non-commutative algebra. Here symmetrization is given in terms of curvature variables. So you take symmetrization map, but you involve only hat variables. So this will be by construction basically in the image of differential. That's why you can speak about the corresponding chain of transgression and use characteristic homomorphism construct an output of a transgression. And then to prove things, you should chase this big data. So unfortunately, I will not present most of this diagram, but just show you how bad things or nice things. So you have this main object non-commutative algebra, you have this quantum and classical one, you have a bunch of transgression maps, and you study the interaction. It's not even cumulative diagram, but it's a nice diagram that explains what is going on the 30 pages in the paper. So it does not commute. Well, to make it commutative, it's in some places it commute in a certain sense. You should change some notation to make it, because sometimes some maps takes values only in the subspace and so it commutes, but you should make it even more beautiful. So I hope it gets converted up. But it's a nice generalization. So basically, we're using universal property of these guys and some homotopy methods. So we construct a lot of homotopy operators. And you can do the same now for the context of symmetric pairs. So you just take relative versions of all viral algebras. So you take a corresponding basic subspaces, for example, for Hermitian algebra, if you look like this, and you have the projection, and then you define transgression maps with values here. Now you should be a bit more careful from which space you transgress. It's given here, so more or less you generalize the same definitions to the is a bit careful to the case of symmetric pairs. And you can quantize this and you can prove the nice version of the transgression theorem that these relative transgressions are restrictions over absolute transgressions, so transgressions in the whole viral algebra, which allows to give us the following definition of a primitive elements with restriction over primitive elements in G. And then using some magic is a Serre-Hochschild vector sequence. You should look at the second page of it. You can prove this fact that this restriction is non-zero and we know the dimension of it. And it's a give us relative version of a transgression theorem for the cases of our interest. As I said, only in these cases, this will be non-zero. So we prove the relative transgression theorem. And we can, using that,
How much time do you need?
maybe 20, 15 minutes.
15?
15? Okay. Yes. Great. So the same could be now, as I said, done in the context of quantum viral algebra. So basically, and more or non-commutative viral algebra. So you define it in the same manner, and then be able to prove these theorems that again our primitive elements could be interpreted as image of a transgression map for a Clifford algebra isotropy representation. So some quantization of a relative transgression map. And remember, I was telling you that it was some important result by Cartan that he was able to prove using that big diagram that I showed you. And it's another conceptual proof even the abstract. All right. Now, next ingredient will be Hertzian projections. So, about Hertzian projections, you can think about it. So, let me define them and then we'll focus. Let's look first at the case of just the algebras. We have a triangle decomposition, positive, negative roots, concept algebra. Then we can decompose our Clifford algebra in the following manner. So we know that this is orthogonal decomposition with respect to form. So that's why we can write it like this. Then we can, of course, project along this ideal, well, along this subspace. In general, it will be not an algebra map. But if you will restrict to invariance, then it will be algebra map. Moreover, it will be isomorphism, and moreover, you can make it filtered algebra isomorphism, but you need to add some special filtration on the Cartan subalgebra using some principles of embedding, and that will maybe comment a bit more. So it's due to, it's called Clifford algebra conjecture by Cartan that was proved by Joseph and Alexei and Pavlov. All right. So how you can think about these Hertzian type projections? So remember definition of a Clifford algebra. So I'm going to here again. So G. So we caution our tensor algebra of G by the following value of x tensor y plus y tensor x minus 2 bx y. So I could formally insert a parameter here, right? So when t is equal to 0, you will obtain just exterior algebra. But if you will look at the limit at the highest value of t, so you have some element in Clifford algebra, you look at the power of t, the highest coefficient of the highest power of t of this element, this will give you exactly the Harish-Chandra projection. So it's sending, it's another limit of this deformation. So we are looking not the classical limit, but of behavior of our deformation at infinity. So this is more or less the meaning of these Harish-Chandra type projections. So you're looking at the high values of the deformation parameter. Okay, this construction is due to constant. Then we can do the same for our symmetric pairs. This is just recording what is W1. Remember, it was minimal constant representatives of the quotient of two quantums. Every element of this space defines you a way how to extend positive roots of K to positive roots of G. It's not necessarily unique. So let's then know this positive root system T root system of G by this space, and we have the corresponding triangle decomposition now, which we can go intersect with our isotropic representation, and now have the similar decomposition Clifford algebra isotropic representation, and play the same game. So now we can prove this theorem. So it will be now not algebra isomorphism in general, but subjective algebra. Because guys here has would have anything, some algebra projection as we've seen on the previous slides. Okay, I will skip the sketch because it's very nice, but fortunately I don't have time. So we extensively use the transgressions and Harish-Chandra maps. And the last thing that I promised to say for is this filtration of the Cartan algebra. So again, I'm going back to the result of two conjecture by Constant that was proved by Joseph Alexeyev. So one could show that Harish-Chandra map sent our primitive invariant, well, quantization of that, to exactly Cartan's algebra. So the linear density. All right, that means that we can define the iteration on this Cartan's algebra. Well, we know that the primitive elements, it's a graded subspace. So we look at the image of all guys of lower. So it will be very nice iteration. Very natural from this. But we can also define iterations. Look at the dual root system and look at the Lagrange dual. So basically what you do, you look at your Dünken diagram in reversal manner. So for example, for a cell, nothing will change. For O and SP, so O will become SP and vice versa. Well, O. So you have a principal SL2 embedding in the corresponding Lagrange to the algebra. What is the principal one? So it means that the H will be a regular element. Or you can think about E as a sum of all three fluids. Then you can decompose your real and have this isomorphism. And you can look at the coordinate action of this element E, this important element, on H star. So you define this iteration in tricky manner. So it's minimal m such that this will terminate. And it was a crazy and surprising conjecture that these two iterations coincide. So one comes from geometry. So remember, it was the degrees of the homology of our Libra. This is completely algebraic. So these two filtrations agree. So it's now not a conjecture, but a theorem proved by these fellows. And we can formulate it for the case of symmetric pairs in a similar manner. So first we prove the statement that if we take our relative primitives, it will give us part of Cartan subalgebra that is in P. Then we define the filtrations in the similar manner. So one comes from this geometric setup, another comes from algebraic setup in the same manner. And these two filtrations coincide. Surprisingly, this looks like some algebraic form, but there is some connection with the high familiar spaces that I don't know, but want to highlight familiar spaces. And yeah, what to do with all of these things? So we have the main theorem and some amount of tools that was developed in the process. So it should be related, and we are working on some generalization of different Cartan models to compute some equivalent homology. Of course, this is closely related first, especially for quasi-Poisson geometry, because our phi is one of the key ingredients of Cartan frequency there. It should be some space on open question of cohomologies of modern spaces of flat connections. There is some nice applications towards Schubert calculus and quantum cohomologies of these spaces. It's a content of another paper. In fact, you can construct, you can derive roots for example, Schubert calculus and Rosmanians using Clifford algebras. And we hope that this quantum moment will allow us also to recover a quantum cohomology of the spaces. Recall that, for example, on Rosmanians, the coefficients in Rico cohomologies given by intersections of some Schubert subvarieties. In quantum cohomologies, they are given by some Gromov-Bitten invariants. And it looked like, after we will produce some in the case of quantum groups, these techniques could be applied to the quantum deformation of this. So I hope maybe this thing could be available for L infinity. I mentioned these curvature variables, and the whole setup, I think, could be from Lie algebras could be generalized to L infinity. I don't think that anyone with this. Some open programs. Of course, algebraic general operators, some induction functors, and as a case for quantum groups, we have some preliminary results. I actually was speaking about it a couple of years ago here, and we have analogues of these theorems in very simple examples, but I hope soon I will get some more. So, thank you very much.
Thank you very much. Questions? Can you about maybe this? I think it connects to multiple of those. So here you said quasi-Poisson geometry and Lie spaces, and also gauge theories. Can you say this morally how I don't know the quantum well algebra or the relative case should fit into fit with?
Well, for the relative case, I don't know how to. Maybe, well, one should formulate some analogues of, Cartan geometry, but this L infinity guide, so you can construct well algebras for L infinity algebras as a corresponding causal algebra, and then you will have the nice set of generators to this curvature from our Cartan elements. Yeah.
And for moduli spaces, so these should just correspond to cohomology.
Yes. Actually, so how it works? You can identify the cohomology classes in the modular space as chains of transgressions in the quantum biology. Okay. So I think it was done again by Manrique and Alexey. I'm not sure. And there is some open questions about how to multiply these guys.
And when you also mentioned group valid moment maps, you were saying that you would be able to, let's say, do group valid moment map reduction for these analogues.
So it was the talk one can make here when we were speaking about this group valid moment map. So basically, yeah, how to see directly from here? It's almost started.
So it comes to this point with Schubert calculus and probabilities and solutions, plotting the dimensions whatsoever. You mentioned typically in order to compare those, you need to have something like a local signal or block. Is it all these situations like with the setup that we consider?
Yeah. So I just know there is some work in progress. So for example, for Grassmannians, the quantum cohomology is computed. Yes, and there is some variable, but what we're interested in, so we have a description of regular Schubert calculus as some graded version of invariance in the Clifford algebra. Now we want to see if so we have another deformation of a Schubert calculus. So we want to see, is it the same as a quantum cohomology, and then it will be another way to compute it, and it will be a very strange basis there. But so it's on by this point, it's very naive idea that, well, maybe it works, and we have some powerful algebraic setups, and we want to see what is geometrical about.
So similar argument be applied to the cohomology of quantum resonance.
Yes. You need one thing. You need a direct.
Okay. Well, I have that you want there.
So basically, everything is almost ready because you need quantum Clifford algebras, but that's fine. We can do that. So then you need a Dirac operator to show that you basically need to show the following things. You have your, let's say, Grassmannians quantum Grassmannians, right? You have your calculus on the Grassmannians. You should show the following isomorphism that is isomorphic to the invariance with respect to your quantum group. Well, now I will use 5. Then you can transfer it to the local region.
I think what happened too.
Yeah. That's why if you have a Dirac operator, you have everything, because Dirac operator will using Dirac operator you can prove this. And then you can construct some Clifford algebra of this body. So quantized Clifford algebra. And then taking the graded version of this.
Like you said, we can graph for the two forms.
Yes. But yes, no. So I hope soon we will do this procedure for spheres, and it will be related to quantum Clifford analysis. But basically, the strange thing what's happened when I know how to construct quantum Clifford algebras, that turns to be isomorphic to the classical one, but in a very strange manner.
Okay.
And that's why, well, there is some work to do, but it's like a research plan how to improve it. And this is connected to this true cloud moment. Because
Maybe a quick question. So we mentioned at the beginning that stuff doesn't work for E6 and SP8.
yes. Because Well, we use some trick. I think everything should work, but our proofs are not yet completely perfect to cover this. We have a very exceptional example. So I think the statement of the theorem will be still true. The way how we prove it.
Is it because you use something that uses the fact that there is classical groups involved, or?
Yeah. This is nice result, for example, for the case of ON. So when K is ON, you can show the following, that the invariance of the Clifford algebra is just its Clifford algebra on the primitive element. But if you will look at, so it's disconnected group, right? And I will put it. But if you look at the invariance with respect to the algebra, it will be a bit bigger. It will be again this Clifford algebra times the algebra of projections, which will be two-dimensional in this case. So this thing is not invariant with respect to disconnected group. Okay. And then using some Harishchandra maths, we can show that this the representative of disconnected component switch to basis elements here, and then it allows us to prove everything very nicely. For the last, for the exceptional group, it will not work like that because you can look at the disconnected component, corresponding disconnected group, but the algebra projection will be bigger. And also another thing that is a bit more maybe conceptually, not conceptually, but technically stronger. So here we use some second page of their Hopschild spectral sequence. And in this case, the pair proving, it's very nice. For E6, E7, it will be a bit tricky.
I see. Okay, thank you. Okay, any final question? Okay, then let's take it again.